So yeah, thank you, Sandrine, for I think you've addressed most of them. So
yeah, there are just two new questions. I think.
2 new questions. Okay, okay.
Well, now 3.
Are there some questions that are unanswered? I think Samira, you had some specific questions, and you mentioned that you will be need to go in 10 minutes or something. Samira, is there? I think you had some questions about the. What was it? The labeling, I think.
Yeah, I discussed with her that.
Okay.
There was, I think, a last question on the segment gray matter and DTIFA images.
Right. So
the last 3 questions are unanswered.
Right. Okay. So we'll start with Hans Scott. I saw SCT as motion directional images, but can it also correct for physiological measures like pulse respiration? So no, there's no tool to do that. Well, I mean, I think there was. So there is no like direct tool to do that, but it can extract some signals that could then be used to accommodate like physiological noise correction. I'll point you. Let me just share my screen again. Remember, there was someone asking something similar in the forum. Something about time series. Extraction of voxel time series per spinal level per GM tract. So that's exactly it. So yeah, so that's an example of signal extracted from an fMRI time series in specific location of the spinal cord. In the gray matter in that case. So, you could use SCT to extract that information, put it in a CSV file, and then reuse it somewhere in your analysis, for example, right? So SCT has not been designed specifically to do that, but you could still, find some workaround if you want to stay in the same ecosystem. I don't know if that addresses your question, Scott. Who are you, Scott?
Yeah, thank you.
Yeah, okay, good. So question not related to analysis, is there a way to convert the mesh VTK to an STL5 for 3D printing? Yeah, we've had something like that. I think Alexandru.
Yes, sorry, I just joined. Yes.
No worries. Yeah, it's a question about converting the VTK to an STL5 for 3D printing. I think we've done that in the past.
Yes, we managed to generate the surface.
Yeah.
Yeah.
So yeah, so maybe you could answer look into this and answer the participant.
Yes.
Right. Yeah. Free software can do that. It's true. So some questions about the segmentation. In the case of traumatic spinal cord injury, it is difficult to distinguish the tissue from the CSF. Getting out the shape of the high signal of the remaining tissue on T2-weighted images. T2-weighted images alone. So I'm not sure I understand the question. So the question is basically in some cases, because of compression and lack of CSF, the segmentation leaks, right? Or like there's a sub-quality of the segmentation. In that case, you might need to do some manual correction. And we are currently working on multimodal, multi-contrast segmentation methods. They are not ready yet, but it's a plan. have it ready at some point. Question number 2 is when segment. So does that answer the question? Noboru, I don't know who is asking the question here. Noboru, are you here?
Yes, I'm here.
Oh, okay, it's here. Okay, great. Question number 2. When segmentation is performed on an image, the color portion, right, spinal cord and coda echinea are recognized mixed together. It's, yeah, I agree. It is tricky. I've run into some difficult segmentations in this location. I'm afraid I don't have good news for you. As of today, we have not really, since there was very few requests to focus on that particular area of the cord. We have not spent a lot of effort developing specific tools that are robust for this part of the lumbar and sacral cord. But we could train models to be able to work better in this area. If you're interested in that, what I would suggest is that you reach out to us via email, or maybe open an issue on the forum, and then we can dedicate someone in the team to develop a specific model for that. But it will not be done in 2 hours. It's like probably a couple of weeks project, but it's a good idea. If there's a need for it, then we can make it work.
Thank you.
Question number 3. Spinal cord extends to the vertebral body at L2. Speculate this due to right and registration. Right, interesting. To force the registration without the level of the posterior number, the vertebral area of L2 will be compressed. Okay. So I'm not sure I understand this part. L2 vertebrae will be distorted. By distorted, you mean that if you want to register, okay, if you want to register your spinal cord images from like a typical Japanese person, or like a person where the spinal cord extends below the L2 vertebral level, then that registration will misplace the actual location of the spinal cord, because it's based on the vertebral levels and not the spinal level. Is that the concern?
Yes, the spinal cord at the level of the L2 get bent.
Okay.
Yes.
So I have 2 things to say about that. The first one is there a better way? Yes, you could potentially, in this case, do a label. So instead of relying on the vertebral level, maybe you could rely on the actual spinal cord. So if you're dealing with thoracolumbar data, you can identify the start of the coda echinea, for example, label it manually, and then use that as a reference point for the registration on the PAM50 template, for example, or across individuals. And the second thing is, it might not be trivial to do this. So please, reach out and we can guide you through the process of doing this, doing this coda echinea based labeling and registration. And second, I'm not exactly sure, how the data look like, but we could also assist you if you send us like an example, like a typical data with the code that you've been running, and we can see what's happening. Maybe there is there's like a tweak that we can do, because there's a lot of parameters on the registration methods, and maybe some of the parameters might actually overcome or mitigate the problem that you're experiencing, right?
Okay,
I hope.
Yeah. So sometimes it seems difficult for me to understand everything in English. So
sure, yeah, no, I'm sorry. So I'll try to say it again. So so there are two things. Well, actually, the best thing that you can do is maybe get in touch with us, and we'll take the time to to look at your data and to find a good solution for you.
I think.
Yeah.
Okay. Thank you.
Thank you, Alex. What's the best way to work with more ST version on single machine? Right. Yeah, that's a great question. Okay. One stable version which I use for processing. I have then symbolically pointing to one of the version. No, I don't think there's a more elegant workaround, not that I'm aware of. Not for the rest of the team. Oh, Nick is here. I think you should be able to make use of the Conda environment for that. Oh, no, I don't think we want to use the Conda environment for SCT. I don't think I would recommend that, Nick.
No.
Because I think it will create other collateral issues. I would not get into the virtual environment. Like the way I would do this, if I open a new terminal window and I go to the home, there is a file called HRC, and this file is actually probably not show my secrets. Okay. This file is edited during Spinal Cord installation, and it creates a path to your oh no, that's Streaming Toolbox, sorry. Okay, here, SCTDIR. So that will point to your default Spinal Cord Toolbox installation, right? So if you have another one, what you can do is comment out this path, and then have, I'm just going to emulate another Spinal Cord installation. Let's say you have SCT 5.3, right? So if you want to use 5.3, then you would edit your bash RC file, make it look like this, and then comment out this one, and then save it, open a new terminal, and this one will be used. Right?
Okay, well, I'm gonna give it I'll write up an issue for us, and I'll give it some experimenting. I think we can probably make this smoother.
Yeah. Thank you. Yeah, it's always my concern is just that sometimes, like, the concept of containerization and virtual environment and things like that are straightforward for those who understand it, but in some cases it might actually be overwhelming to use those additional technologies. So yeah, I'll stop there. Okay.
Great, thanks.
Any other questions? Any other questions before we move forward with the course? Okay. So, so we can continue then the segmentation, and this time we'll do the segmentation on the T1 weighted data. Okay. So in order to do the segmentation on the T1 weighted data, we need to go into the T1 weighted folder. So I'm gonna go back to the data folder. I'm gonna do an ls and see all my folders here. I'm gonna go to the T1 folder. ls, I can see my T1 file here. And then I run propseg on the T1 weighted data. rct propseg -i. And then this time the contrast is a T1. Okay. You see single subject. And just for fun, I'm going to run propseg on the T1 weighted image, but I'm going to write -CT2 here so that you could actually see what's the effect when you enter the wrong contrast. And in fact, we can do this in parallel. So I'm going to copy this, open a new terminal window, and pasting these commands, and I'm just replacing T1 by T2. So now I have two processes that are running in parallel. Okay. So it takes a bit of time here because the data is bigger. There is also the brain part, so there is much more data to analyze. Eva, I think you are asking if this is recorded. I think it is recorded. Is it? Is it recorded, Rob? I know if Rob is here. Yeah.
I'm sorry, did you ask a question?
Yeah, is this recorded?
Yes, this is recording right now.
Okay, cool.
Yeah, sorry, I just had to make a quick phone call.
No worries, no worries. Okay, so again, we have the facialize window, like the facialize commands that we can copy, paste, look at the result in facialize, and then we're going to open the QC reports. Whoa, funky. That is a bit ugly. And can someone tell me why this is ugly? I actually did a mistake when I wanted to do my comparison between T1 and T2 contrast. The outputs are named the same way. So what I should have done is use the -O for the output and use a different output file for the command where I tried with the T1 contrast and the other one where I tried with the T2 contrast. So that was my mistake. So we're going to do a bit of a bash command here. So I'm going to rename this one wrong. So I can do mv for move, T1 seg, and I want to call it seg underscore wrong to contrast, something like that. Voilà. Which is called wrong. Then I'm going to rerun propseg with the proper contrast, which is T1. And while this is running, we can look at the QC report together. Okay. So the QC report is still here. Okay, that's the one that we've had open before. And now we can refresh it. So if I press on Command R or Control R if you're on Linux, then you can see that there are like 2 additional lines that correspond to the segmentation on the T1 image. So the first one is the ugly one that was run with the T2 contrast. Where is that? And that's the, oh, okay. Actually, T1. Right, okay. So yeah, so they are both wrong because yeah, it's a bit complicated. I'm sorry, I confused everyone here. So what's happening is that while the QC report was generated for the correct syntax, then the other process terminated and the wrong segmentation was generated. And so the QC report is wrong in both cases. But now this one is finished, so I can refresh. And we can see that we now have a proper segmentation. I apologize for the confusion. I basically tried something improvised, and I should not have done that. Anyway, so you see that this is the correct segmentation on the T1 with the correct syntax. Okay. But what you also see is that there is a strong leakage of the segmentation, right? It's looking ugly in many different slices, here, here. And that's because it's using image-based propagation, and so basically the mesh, the 3D mesh, is attracted to contrasts. And what's happening is that there is some tissue that have the same intensity as the spinal cord, so the segmentation is actually attracted to this tissue. Okay, so that's the reason why it's failing. So the take-home message here is that PropSeg can fail if there are some like additional contrasts on the image that could lead to those problems. And this is why, yeah, I have a question.
Is the field of view different between T1 and T2?
The field of view is different. So the T1, as you see, has like the entire brain and part of the spine, and also on the right left, the right left is completely covered. So you see the right left is completely covered on the T1 weighted image, whereas on the T2 weighted image, it goes basically from there to there, right? So we are missing part of the left and right, and also we don't have the brain. Okay. Maybe Sandrine, could you? Sandrine, could you maybe do a note here, because this is not supposed to happen here. Yeah. Yes, Luis.
Okay, and I have one question about what feature is used in this algorithm. Only the intensity of image, or
right? So yeah, it's a good question. Yeah, right. So the features that are used for the segmentation include a variety of parameters. Those parameters are briefly explained in the next slide. So there is a prior for the initial radius of the segmentation. So we assume, if you go to PropSeg, type the help, the default radius is 4 millimeters. So there is a cylinder that starts at 4 millimeter. It's actually the radius, sorry. So the diameter would be 8 millimeter. Mm-hmm. And then it will adapt to the size of the contour. But if you're dealing with like mouse spinal cords, then you would change 4 to a 1, for example, right? Or if you're dealing with like an elephant spinal cord, then you would, you might want to quadruple this, or I don't know. And there are other parameters such as the contrast, as well as some parameters that tell the algorithm to care more about the overall shape versus about the contrast and the intensity of the image. And so we are now really entering the nitty-gritty of the algorithm. We don't necessarily need to do that because I'm going to show you that there is another algorithm which is based on deep learning, which we find to be more robust in those cases. So if you want to know more, I would advise you to look at these articles as well as some of the parameters. But for the interest of time, now we are going to focus into another function called SCT Deepseg SC. I think there was another question. I hope that answers your question, Luis. And
Julia, may I ask if Deepseg is robust compared to PropSeg? In what cases would you choose PropSeg over Deepseg?
Right. So in like most cases of like adult spinal cord MRI, I would use Deepseg, and especially if there is like presence of lesions or compressions, because Deepseg was trained with data from patients with MS or spinal cord injury. However, in some cases, for example, the ex vivo spinal cord or like data where the overall image context is very different, like an extracted ex vivo spinal cord, I would use PropSeg there because it's purely based on image features and does not, recognize as a deep learning model would do when you train a deep learning model with images that are coming from, a living body and an entire body. So for ex vivo spinal cord, I would use PropSeg, and also for like other species like mice, rats, dogs. In some cases, PropSeg works better than Deepseg, but in any case, you should basically try it and see what works best with your data.
Thank you.
You're welcome. So, what is Deepseg? It's based on deep learning, and it is composed of a cascade of two convolutional neural networks, or CNN. The first detects the spinal cord, and it reduces the space around it for more robustness. And the second one segments the spinal cord. So let's try this out. We're going to run it on the T1 weighted image. Okay, so we are in the proper folder. So I'm going to type SCT Deepseg SC. Input would be the T1 weighted image. The contrast is T1. And now I want to specify particular output folder where the image will be placed. So I'm calling it Deepseg. And I still want my QC so that we can compare Deepseg and PropSeg. So while this is running, I can say a few words on the Deepseg algorithm. There are different options. So in the other terminal, I'm gonna run the usage so we can discuss about the different options. For more robustness, you could input a center line, right? So by default, it will try to automatically detect it using the convolutional neural network, but you can switch to another method if it works better in your case. You can also start a viewer where you would click, you would do like a couple of points inside the spinal cord to help the software segment the spinal cord. Or you can also provide a file that already has a center line. Okay, so you have different options there. There are some thresholdings of the output segmentation. If you're dealing with brain, with data that has a brain, then you can select one, and the algorithm will try to separate the brain and then to only segment the spinal cord. There are different kernels, so this is getting a bit technical, but the segmentation can be done with deep learning models that have been trained to learn about the 3D information versus slice-wise 2D information. And some works better than others, depending on the case. By default, I think the 2D is selected.
Julian,
So, yes?
may I ask a question about the 2D versus 3D? I haven't done lots of testing, but on a few data sets at 3T, I was looking at using dash kernel 2D and dash kernel 3D. And I thought that the 3D kernels would be more accurate because presumably it would use some sort of spatial information that if the spinal cord looks like this on one level, it looks similar on the next level, etc. But at least on a couple data sets that I tried it out, the 3D models or the 3D was not doing very well at all. Like 2D was okay, 3D was very poor. So I just didn't continue with 3D anymore. Have there been like some updates in the last year about this, or should I always use dash 2D?
Right. So there's no update in the stable version, but we are working in an improved model that will likely be 3D and also multimodal, multi-contrast. So there will be updates, hopefully in a couple of months, but for now, it's the same algorithm. Yeah.
Okay, thank you.
Maybe, Sandrine, you can also put a note on the fact that we should show what the default is for this option. It's not shown. Thank you. So I'm coming back now to the tab, and we can see that the result is now that the function is terminated. So we can open the QC report that we had before. So it's this one. I will refresh it, and now you see that there is another function that is listed, Deepseg SC. And if you click on it, you now have the result of the segmentation based on the Deepseg algorithm. And if you use your arrow to go up, then basically compare results from PropSeg versus results with Deepseg. And what you notice is that the leakage that we've had previously is now corrected thanks to the Deepseg approach. Okay. Any question before we move on to the next section? Okay, so in this section, registration to template, we'll learn how to register a new image to a pre-existing template and how to use this registration for computing spinal cord cross-sectional area across the superior-inferior axis. So first of all, a bit of theory. The template-based or atlas-based analysis is commonly used for brain studies and requires a template. So in SCT, the latest and recommended template is the PAM50 template, and PAM stands for Polytechnique, Aix-Marseille University, and Montreal Neurological Institute, or MNI. And these are the three institutes that collaborated to generate this template. So the PAM50 template consists of a T1 weighted, a T2 weighted, a T2 star weighted template, as well as white and gray matter probabilistic atlas, as well as white matter atlas of the various tracts in the spinal cord. So there are like 30 different tracts, and we also have, which is something which is not shown here. Maybe something you can add a note on that we should also show. Now we have a parcellation of the gray matter into 6 different parts. So the ventral, intermediate, dorsal, as well as right and left. And since version 4.0 of the Spinal Cord Toolbox, the PAM50 has been put in the same coordinate system as the MNI template. So the MNI template is a popular brain template that people use in neuroimaging studies. And if you open the MNI templates and the PAM50 templates, they happen to be registered together. So they are in the same physical referential system. And this is very powerful because if you're doing brain spine studies, for example, then you can work your brain data in the MNI ICBM 152 template, for example, and your spinal cord data in the PAM50 template. And then you can basically merge your results together into the same physical space, same physical coordinate system. So next obvious question is, how do we register data to the PAM50 template? Luis, I think you raised your hand, yeah?
Yeah, just to follow up on another question I had for you earlier this morning. So these are adults, right?
These are adults,
subjects.
absolutely,
Okay.
Absolutely, yeah.
Right.
Yeah.
Do we know the age range, the demographics?
So I invite you to look at this article that gives all the details of the age of the demographics. Yeah. There are probably a lot of students in there. So the first step for template registration is to obtain the segmentation and then label vertebral levels or discs in order to match the template to the subject's MRI. So historically, 2 vertebral levels were necessary for registering data to the template using the function SCT register to template. But we recently introduced the possibility to also use disc labels instead of vertebral labels in order to accommodate data that were composed of only a few slices centered at a specific disc levels. So if you wish to register data to the template, you can either use the vertebral definition of labels or disc labels. Okay. So the image here shows the convention that is used in SCT for label values. So, if you want to label the mid-vertebral C3, then the label should have the value 3. If you want to label the disc C2, C3, the label has the value 3. Okay. There are also some labels that are like 50, 49, and they respectively correspond to the pontomedullary junction and the pontomedullary groove. And we'll see that this could be used for subsequent analysis as well. So vertebral labeling is done using an automatic method that finds the C2, C3 disc, and then finds neighboring discs using similarity measures with the PAM50 template at each specific level. So it's robust to cases where, for example, like there is a metallic implant in a patient, and so we are missing the information from the discs, but the function should still be, robust. Obviously, it fails in some cases, right? But we are trying to make it as robust as possible to cases where there is some missing discs or whether the discs are closer to each other compared to the average population. And so this is based on a probabilistic distance, from the PAM50 template. And as the discs are detected in a particular patient, this probabilistic model is updated to adjust with the size of the patient. Okay, so the next step is to straighten the spinal cord in order to align it with the PAM50 template, which is a straight template. And this straightening is done by finding each point along the spinal cord, and there is mathematical transformation to go from the curved center line to a straight center line. And so there are two warping fields that are generated. Warping field that is called warp curve to straight and warp straight to curve. And a major advantage of the implemented straightening algorithm is that instead of doing a slice-wise transformation to basically straighten the cord, here the inner geometry of the spinal cord is preserved. And another advantage of the inputting a forward and a backward warping field is that they could be concatenated with subsequent transformation, as could be seen later. So you can basically have sets of transformations that you can concatenate, and these transformations are compatible with ITK or FSL or like other software that you might want to use in your subsequent analysis. So here there's a movie that shows how the straightening is actually done. It's like some sort of a bending, if you will. Okay. So an affine transformation is then applied to match the vertebral levels of the subject to that of the template. And then a non-rigid transformation is done to finally match the subject's cord shape with that of the template. Okay, and this non-rigid registration is tricky, and that's what I was talking. That's what I was saying at the beginning of this course this morning. That it can be tricky to find the appropriate algorithm. That's really what's I would say the most difficult part in using SCT. And any other neuroimaging analysis pipeline is the registration part. It can get very complex. So there is a variety of algorithms that exist, and what you need to remember is that the main difference with brain algorithms is that here the transformation is constrained within the Z direction. So it's basically the axial plane. Okay, so the default transformation should work for most cases, but you might want to play with some of the parameters to optimize registration with your particular contrast, resolution, and cord shape. If you're dealing with highly compressed spinal cord, for example, then you might want to consider algorithms that have much more degrees of freedom compared to the default one. So I'm going to show you some examples, but in general, if you're having difficulties, with the quality of the registration, then please feel free to reach out to us via the forum, and we'll be happy to help. The important aspect from this slide is that the registration can be done in multiple steps with the flag param step. So you can first have like a coarse registration. That would be step equal 1, and then at step equal 2, you would select more a fine registration, like a finer registration based on B-spline seen from ants, for example. Another thing to know about registration is that there are different types of images that you can use for the registration. It's either IM or SEG. So if you have a segmentation of your spinal cord, then you can use that segmentation for as a registration object, right? So you can, instead of using your image, you can use the segmentation. Why is that useful? because if we look at an image, let's open an image, for example, this one. Okay, so let's look at an axial view of the spinal cord. I'm gonna increase the contrast a little bit. I'm gonna remove the segmentation. So in parallel, I'm also going to open the PAM50 templates. Actually, that's going to be interesting. So I'm opening the PAM50 template, which is located in my SCT installation folder. So in my case, it's code, SCT, data, PAM50 templates, and then here we have a list of all the template objects. So I want to open the T1 weighted PAM50 template. Okay, so that's the template. Okay. Increase the contrast. So the ultimate goal is to register this template here to this subject. Okay. And when you look at an axial view, you can see that it can be, and this is a healthy participant, right? In patients, it can be even more difficult. But in some slices, you see that there is poor contrast between the CSF and the outer contour of the cord. It looks like the cord is merged with this conjunctive tissue. And if you try to register to the template only using information from the image, there could be some error, right? Because here there is a clear distinction on the template between the CSF and the cord across all the different levels. So if you use the image only, you might have some errors in the registration. Whereas if you use the segmentation of the cord, which is very well defined, and use that segmentation to register it to the segmentation of the PAM50 template, which I'm going to open here. Let's put it in red. Then this registration will be much more robust, right? And in order to do that, then you need to select the type seg as opposed to the type im. Okay. Pedro, I think you had a question?
Yes. So I don't know if this is in the toolbox and if you have thought about it, but would it be possible to develop a method to do both at the same time, like the unified segmentation of SPM? So you would not to, it would be an automatic thing that you're estimating both the segmentation and the
Right.
transformation.
Yeah. Oh, I see. Estimating both the segmentation and the transformation. So it's currently not. We have a research project on that. It's still ongoing, but we're not sure if this is the right approach. Yeah, we are considering this and validating whether this gives better results than the current two-step approach. But one thing that we could do, I know that doesn't really answer your question, but is that we can combine the image and the segmentation within the registration process.
Great, thank you.
Yeah. So bear with me. Again, this is the hardest part of the course. So we're going to do some a bit more theory, and then we're going to try it together. Okay. So the following warping fields are generated after the registration procedure. There is a warp forward and a backward registration field. And what we mean by a warping field, it's basically a 4D volume that contains displacements for each pixel, right? And so what's getting a bit confusing is that there are different software ecosystems out there. There's the, I would say, the ITK-based ecosystem, which ANTS and SCT are using. And these ones are defined warping field with 5 dimensions, whereas the FSL, SPM, and I think AFNI as well use 4D warping fields, right? And so if you're generating a warping field with SCT and you want to use it in FSL or SPM or AFNI, then you will need to convert it using these commands. Okay, SCT mage, and then to FSL, and that will create a warping field that is compatible with FSL or SPM or like the other software. Okay. So once the subject is registered to the template, template objects such as the white matter atlas, the gray matter atlas, they can be warped on the subject space. And metrics such as magnetization transfer ratio can be extracted at specific levels and in specific white matter tracks. And also cross-sectional area can be computed and averaged across the desired vertebral levels, because now you have information about the vertebral levels. And so you can say, I want to compute CSA between C3 and C5, for example. Okay. So this is the kind of things that we're going to generate in the next couple of minutes. And these are examples of quantitative results that that we'll be generating. Right, so CSA across the spinal cord, CSA of the gray matter across the spinal cord, and then various metrics in the white matter tracks. I think Pedro, yes, you raised your hands. Yeah.
So just to understand, so the segmentation of tissues is not automatic. I mean, it's based on registration, but it's not estimated based on voxel intensities, like in the brain, isn't it?
Right. So it's a key question. So the segmentation of the spinal cord is based on the intensity of the pixel. Okay.
Of the tissues, like white matter, gray matter.
So okay. So what we've seen so far is that PropSeg and Deepseg can only segment the cord, not the gray matter. There's another function which we're going to see later in the course that can segment the gray matter, but that's about it. We are not going to segment the cortical spinal tract specifically. We only estimate the location of the cortical spinal tract based on probabilistic atlases that were done in tracing studies from ex vivo data. So this probabilistic white matter atlas is really based on previous work from the literature from tracing studies, because so far there is no method that enables us to know exactly where the fasciculus gracilis, cortical spinal tract, rubrospinal tract are located for each individual patient. And it's the same with the brain, right? When you do brain studies, you don't know exactly where the corona radiata is located, right? What people do is that they would do a diffusion scan, get the tractography, and then from the tractography pathway, they would estimate the likelihood of the location of the corona radiata, but we don't see it with MRI. We can only estimate it.
Oh, no, that's right. So no, but I think that's not exactly my question. I mean, of course, when you do atlas-based segmentation, you're based on something, and of course, it's based on registration. But I was talking specifically about gray matter and white matter.
Okay. Okay, I see. So for gray matter and white matter, that we segment, and that's what we're going to see later in the course.
Okay, thank you very much.
Okay. Any other question before we start the hands-on? All right, let's do it. So we will go to the T2 folder. CD T2, okay. And now we're gonna run SCT label vertebra. So I can do a tab completion. Maybe I can just do it like this. It's gonna be easier. -I T2 minus S is my segmentation. Okay, the segmentation that we computed before. The contrast is T2, and I want my QC report. So this algorithm works by straightening the spinal cord first. It gets the center line. So the more slices you have, the longer it is. Looking at the questions from the chat in between. Oh, thank you, Malo, for statistics and the demographics for the PAM 50.
Julian, I just want to clarify something.
Yeah.
About 2 years ago, when I used Spinal Toolbox for the first time, I think I had to manually create a mask. So draw a dot on like intensity equals 2 for like C2, and another dot intensity equals 3 for C3, and save the mask, and then use that in my like SCT register to template. We're pretty much doing the same thing, but now it's just automated, right?
Right, it's automated, unless when it fails.
Sorry?
Unless when it fails, and so when it fails, you need to basically manually correct the vertebral labeling, and then run that manual correction for the subsequent analysis. But in the best ideal case, it should be fully automatic. Yeah.
Okay, thank you. And is it pretty obvious when it fails? Would we see an example of that today?
That is a great question, and we are so. I can probably like, so in the last part of the course, when we tried SCT on our own data, we can test a variety of data, and then we can explore some of the failed cases. Yeah, absolutely. And the way you would check for this is what we're going to do now. We're going to open our QC report as before. So going to the tab of my QC report, that's my QC report. I'm doing a refresh. And you see now that there is an additional line corresponds to the vertebral labeling. So going down, that's my vertebral labeling with the QC reports. And then I can assess whether C2 is correctly placed, C3, C4, C5, and so on.
Oh, okay, thank you. And if this did fail, then I would go back to my manual like labeling method. That's the only other way.
That's exactly the plan. And in fact, that's the purpose of the next slide. In case there is a problem, you can resort to different options. Either you can initialize the C2, C3 disk, because sometimes the identification of C2, C3 does not work. Okay. If you're dealing with thoracolumbar cord, obviously you don't see the C2, C3 because it's not included in the field of view. So in that case, you can also identify the disk that is located in your data. If you know that you center your FOV at C11, like at T11, T12, for example, then you can create a label with those options. So again, there is a lot of approaches for doing that, and some are covered in this course material, some are covered in the SCT forum, because many people have had the same questions in the past. So I really invite you to look at the forum, reach out to us if you want to do things that are not covered in this material.
Thank you, Julian.
And so that's exactly what you mentioned, doing the vertebral labeling using manual intervention. And that's something we can try now together. So I will create labels at C3. Oh, sorry, no, this is not manual actually. No, this is not manual. Forget what I said. So we just labeled the different vertebra. Okay, so we have this now. We have this image now. And we're going to use this image to generate two labels centered in vertebral bodies, C3 and label 9, which corresponds to T2. Okay. So we're going to do that. We're going to use label utils, CT label utils, T2 seg label. So that's the labeled segmentation that we just created. I want to create labels at the middle of the vertebral body. So that's what we're typing. We want to do label 3 and 9. And we want to call this T2 labels vert. Okay. And then we want to create a QC report to visualize those labels. I'm going to copy and paste this command. Okay, now let's open our QC report. We have a new line here, SCT label utils with the two labels that we just created. Okay. Any questions? Ah, yes. Question from Luis, right?
Yes. So I noticed that when we run this utilities, it uses every core available to it in my computer. Is there a way to constrain how many cores it uses from the CPU to run it in parallel?
Right. So so you're talking about yeah. So if we want to use the so the multi cores are used for the registration to the template, for example, with ITK routines, and there we can use a particular flag to force it to use only one core if you want to process multiple subjects in parallel. I'm going to show you now how to do that, but then we can go this into more details later in the course because this is what we're going to cover. But just to answer your question right now, it's going to be, so it's in SCT run batch command. And the flag you're after is ITK threads. It's basically it sets this shell variable, which defines the number of threads that ITK-based programs will be using for higher performance. So that's something you can modify if you want. But yeah, so let's go back to our registration. So we're here.
There was a question also in the chat, I think.
Okay.
From Tom.
Tom,
if you go up.
For interpolation, for the labeling, are you wrapping? For interpolation, for the labeling, professional labeling. I'm not sure I understand the question, Tom. Could you maybe comment?
Yeah, sorry, I just noticed when you were running the command before that it used the nearest neighbor interpolation when it walked back. I've been reading some posts about interpolation for labeling, and I was just wondering if you used a different one, or do you wrap ants apply transforms in SCT, or is it your own command?
Yeah. So, right. So, SCT apply transform is indeed is a wrapper of SCT apply transform, but only for some types of images. Labels are a bit particular. We don't want to use trilinear like spleen sync, just because we want to keep the integer values of those labels. So yeah, so that's what you're saying here actually.
Yeah, the one above. Yeah, maybe I'm just sorry. I was just looking at that one.
So so this has been applied to the labels, and we do that in order to yeah. So use nearest neighbor, as I said, because we want to keep the integer properties of those labels. For some other data, like the images, we use trilinear or sync interpolation. Yeah.
Okay.
Okay, so let's continue our adventure towards the registration.
Julian,
yeah,
can I have a question?
Of course.
Yeah, I would have a question regarding SCT label utils. How many labels do you recommend to use or create? Only 2 or as many as possible?
Right. That's that's a very good question. So I don't know if I have a slide on that.
I think we have some info on the website. I can find it.
Right, we have some info on the website. So the short answer is that it depends. It depends on what you want to do with the data. For example, if you're interested in extracting microstructure information with DTI in level C2, C3, then you only need to label C2, C3, right? You don't care about the rest. And if you're interested in extracting information between C2 and like T5, for example, and you only use 2 labels, one at T2 and one at C2 and one at T5, then you know that C2 and T5 will be properly aligned, because that's what the registration will do. But in between, there might be slight displacement between the PAM50 levels and your actual participants. We're talking a few millimeters in general. Right? So that might not be a problem if you aggregate your metrics across this entire length, right? But if you want to report the vertebral-wise values, that could be a problem. In that case, I would recommend to use more than 2 labels, right? Now there is a cons in using more than 2 labels. If you use more than 2 labels, then the upper part of the label and the lower part of the label will be chopped off in the registration, which is why currently we don't, by default, use more than 2 labels. Why is this chopped off? Because it's easy to compute an affine registration between 2 values, but if you have more than 2 values, then it's no more affine, right? It's non-affine, and the fact that it's non-affine makes it that there is unknown values above and below, like above the top label and below the bottom level, right? So unless we do some extrapolation of the field, which we don't do because we don't want to generate wrong information, we simply chop what's on top and what's bottom, the top and the bottom labels. Sorry if it was a bit complicated and confusing. Again, there is more info on the website maybe Sandrine, you can post the link. Oh, you posted it already. Thank you. But yeah, no, this is
it's clear. Yeah.
Yeah.
Great for
Okay.
great explanation.
Okay.
Yeah. Thanks.
Good. So manual disk labeling. So yeah, so that's if you want to do it manually, you can basically do so with this window. Actually, let's do this together. CT label details. C2 create viewer. I want to label the disk C2, C3, C3, C4, and so on. I'm gonna call it labels disk, and yeah. So this opens a window, and then it asks, for the labels 3, 4, and 5. And if I make it wrong, then I can do an undo and place it again. Once you're done with this, you can save and quit. And the label disks are created. And you can see them on Facelize, for example, or any other viewer. So you see my labels are there. You can put them in color. So this is the label number 3. That's label number 4 and number 5. Okay, so that's how we create manual labels with SCT. Okay, so now comes the time to finally register our data to the templates. So we're going to run the function called SCT register to template. So it looks like this: SCT register to template. My input is the image, T2 image. We also input the segmentation, so T2 seg. We also input the labels that we created before, the vertebral labels. So labels vert. The contrast is T2, so we want to specify the PAM50 contrast that we're going to register our images to. You can use T1 or T2. And we want to also generate a QC report of this. So while this is running, I'm going to explain to you what's behind this, because I told you before that it's a multi-step registration, right? And at step 1, step 2, we can specify different options. So let's look at the default options for this function. I'm going to look at it in another terminal window. So I'm going to type SCT register to template, and it will show me the different options. Okay. So these are the parameters by default. They are shown here. The first step is to do a coarse alignment with the template space. Then the next step is to use a combination of the image and of the segmentation to find the center of mass of the spinal cord segmentation, and to also find the rotation. So if the participant has the head that is turned like this or like that, the spinal cord will be slightly rotated, right? So this will be accounted for by this algorithm, which is called center mass rot. So it finds the center mass, and it also rotates the spinal cord if needed. And once this is done, the subsequent step is to use the segmentation with the B-spline scene algorithm. So B-spline scene is a regularized scene transformation, which has a lot of degrees of freedom developed by the ants folks. And we use the mean squares metric because we register the segmentation. If you were to use the image as opposed to the segmentation, then you don't want to use that. Instead, you want to use the cross correlation or CC. Okay. So again, this is getting a bit technical, but some of you who are interested to look into those details and to play with those parameters, I recommend that you understand, what are the main parameters that have an impact on the quality of registration. This is the number of iterations, smoothness that you want to apply, the velocity of the registration algorithm for each epoch or each step. You can choose to constrain your registration on a slice by slice basis or not. Okay. In this case, we did not. Yeah, so these are, I would say, the main parameters that have an impact. And these are the default one, which is why I did not have to use the param flag. I just let it by default, and because usually works in most cases. Okay.
Sorry, Julian.
Yeah, Tom?
If I wanted to change one of those parameters, what would the flag be like if I wanted to change anything?
We'll do that together. Yeah.
Oh, sweet, thank you.
So when I rerun this, with param step 1, this, for example, site Deepseg, algo will be this one, and then metric, we will take this one as well. Oh no, we don't need this actually for Santana as well. So yeah, we should be good. And then step 2, so you separate the steps with those 2 points here. Step 2, we're gonna use the image as opposed to the segmentation. Okay, and we're gonna try to see what's happening then. The metric, we're gonna use cross correlation. How do I know that? In order to know what are the parameters, you can see register multimodal function. This function will list all the parameters that you can use. Okay, so I'm gonna open it on my 3rd tab. These are all the parameters. So metric is the flag that we are currently defining, and in this case, I want to use CC, which is the cross correlation to compare images based on their intensities. Okay. So I'm coming back to this tab, metric equals CC. What else? We need to define the algorithm as well, right? So algo equals, instead of using the B-spline scene, I'm going to use the scene algorithm, which has more degrees of freedom. And you'll see that the deformation will be larger. Number of iteration, let's put it at 5. Slice wise, let's keep it, let's put it at 1. So it's going to do a slice-wise registration as opposed to a 3D registration. Yeah, let's try that. Oh, and we also want our QC report, so it's fine. It's there. Good. So I'm running this.
I was going to ask if you could copy that line in the chat.
Oh, yeah, sure. Oh, actually, I'm talking to a single person here. I should do it to everyone. Okay, should be there now.
Julian, I have a small confusion.
Can
I ask?
Speaking. Oh, Lisa, yeah.
Okay, so T2seg that you use is from PropSeg using T2 contrast from before, right?
Yes, that was PropSeg. That's right. You're absolutely right.
But then in the future, you said that for somebody like me doing MS research in humans, Deepseg is better. So I should use that
Correct.
output. Is
That
there
is
a reason
correct.
why Deepseg was done using T1, but everything else is done in T2? Or should I have done Deepseg using T2 contrast as well? So moving forward, I can just use T2.
Just use Deepseg with T2. The reason we show the reason in this course we use PropSeg is because it's just for educational purpose. We start because, and also historical purpose. So PropSeg was the first algorithm that was available, and historically the course only had PropSeg, and then Deepseg was created. So we wanted to show the comparison between PropSeg and Deepseg. So that's why there is a bit of a mix between the two commands in the course. But moving forward for your study, I recommend you start with Deepseg and see if you're happy with it.
Okay, so use everything T2 contrast with Deepseg from like all the way down to what we've done so far, right?
Exactly.
Thank you.
Exactly.
Julian?
Yes, Rob?
Just a comment to everyone, the way that I call these functions is actually in MATLAB. And just in case anyone is like, in love with MATLAB and has lots of MATLAB experience, calling these functions using the MATLAB Unix command works well. So I have all my commands and I can have it automatically look through directories and have text files of all the directory names. And then I call 0 commands from SCT from the Unix prompt. They're all done through MATLAB and I have no problems.
Yeah, thank you, Rob. It's actually a very useful command. Yeah. Okay, so this is done. So now let's go to our QC report, refresh, and you can see that now we have 2 additional functions. So let's look at them. So that's the first one we run. Okay, you have all the parameters here. And then if you flip back and if you use your right arrow, you can flip between the registered templates and the actual subject. So that's our subject, and that's the registered template. Okay. So things to look out for is making sure that the spinal cord is properly rotated on the template, which is the case. I recommend you use the cursor, to make sure that the boundary is correct between the cords from the template and the cord from your participant. And let's compare it with the second command that we run. You can see how crazy the difference is. Right. So what you notice, so I'm flipping between the first command that I run with the default parameter and the second command when I added those funky parameters with the scene algorithm and 5 iterations. So some of the things to notice is, first of all, that the spinal cord here is not properly rotated in the second command. And that's a problem. Now I'm flipping back and forth between the actual participant and the registered template. So that's wrong, right? If you want to warp white matter tracks and then get the metrics from those white matter tracks from the template, then you're gonna make some mistakes, right? In some other location, like here, for example, the registration is fine. Okay, and it's the same if I go back now to the other command, the first command, it's also fine. But it looks like the spinal cord is slightly bigger, but you also need to be careful that there is some visual, perception effect because the CSF is more prominent in the PAM50 template compared to this particular subject, right? So what you need to look out for is really the contour of the spinal cord and not the CSF. Yes, Luis, you had a question?
Yes, so the difference between the last two results there, we changed the metric, we changed the algorithm, and we changed how many times we iterate, right? So I was wondering how much each of these changes contribute to these results not being as good.
How much this difference contributes
right.
to the results that we're gonna compute down the line?
Okay.
Right. So yeah. So I guess it depends. It depends what we do. So if we compute the cross-sectional area, it will not affect the results at all, because for cross-sectional area we are only using the vertebral levels and the segmentation. Right. If we want to compute, if we want to extract values within the white matter tracts on this image, then this is going to affect the results. Will it affect it a lot? It depends. If you're only focusing on the location where the registration is very different, on only like 5 slices, then results would be very different. If you're looking, yeah, if you're looking at the all the slices, then differences might be averaged out.
Right. I guess I misspoke when I said results. I was talking about the results of the registration. So it looks very different, right? The one we use with the regular parameters or your default parameters versus the ones that we modify the parameters. I guess my question was, since the registration is so different with the modified parameters, which of these 3 major changes that we make is the one that contributes the most?
I see what you mean. Okay. Yeah. Right. So I think that the scene algorithm is like a big has a strong effect in the deformation of the cord. It has like those like fine warping that we see here are like very typical of the scene algorithm. Another thing is the metric, obviously, because we are not using the segmentation anymore. We are using the image. So that also has like a very, very, very strong impact on the results, right? In this case, we're using the image. In the other case, we're using the segmentation. So it's not shown here because these are the default parameters, but that also plays a big role. And that's why, in general, I recommend to use the segmentation, assuming the segmentation is good, because you don't have to bother with potential artifacts in the image. Like a lot of images can get artifacts, and those artifacts can have an impact on the quality of registration. If you have 5,000 subjects to deal with, you don't want to go through the. You want to have a pipeline that is as robust as possible, right? So
let's say we use the default parameters and we only modify the iterations. Instead of the default 3, we use 5.
Yeah, that will minimally affect the results.
Minimally affect it. Okay.
Exactly.
Thank you.
Yeah. Other questions?
I have a question.
Sure, Malo, yeah.
I was wondering, for the QC, there is only it's only visually there is no measure like a bias or I don't know, like kind of overlap between the segmentation and the atlas or stuff like this.
So it's a bit of a chicken and egg problem, in the sense that the registration algorithm is using metrics that are defined notably by this overlap. So you could have information about the quality of the registration from the actual output of Where is it? Research template. Right. Right. Yeah. So the output of ANT's registration gives you the matrix of overlap between the segmentation of your subject and the segmentation of the Plan 50 with a mean square metric. Beyond that, now what I recommend is visual visual QC. Yeah. But again, if you're dealing with like large pipelines, you can output you can compute the overlay between the Plan 50 segmentation and your subject segmentation as like a metric that you can then automatically QC for if it's below a particular value. Right?
Okay, and I was wondering more in general, not especially on segmentation, but also for the raw data to see if there is bias or if there is a signal to noise ratio or stuff like this. Like with Cat12, you have like a report with some information.
Yeah, that's a good question. So there are functions that are not covered in the course. Maybe Sandrine, if you could add a note, we can do it in the next course. But there are functions to compute the SNR, which is called SET compute SNR. So computing SNR is quite complex. There are people who spend their entire life, doing it the right way, because we are using multi-array coils. There is relay noise. The way you combine the elements will give you a different version of SNR. A lot of vendors apply filters, which will also affect the SNR. So SNR is a very difficult metric to measure reliably. But so we do offer a couple of methods to compute the SNR. So I invite you to look at them. If you have any issues, if you'd like us to clarify some of the commands, feel free to post something on the forum, so we can elaborate on what method would be right for you.
Julian, sorry to interrupt again. I just noticed at the time we're supposed to be taking a break around now. I was actually just so enthralled I lost track of time myself.
Okay, I think let me check here if it's the right moment. So we just did registration to template. I think it's good now. Yeah. Let's take a break until 1:30. Is that right?
That is correct. Yes, 1:30.
Excellent.
All right. I will stop the recording now.